Hi everybody, and today I'll be going through the pre-lab lecture, mini lecture for a lesson in density experiment. This one should be much shorter than last week. So first, let's talk about what is density. Again, I mentioned this a little bit last week. Density has the formula density equals mass over volume. Mass is usually in grams, volume is usually in milliliters, but any mass or volume unit technically will give you a density. And the definition of density is mass per unit volume. And so we briefly discussed it a little bit last week. This week, we're really going to go into what is it, how can we measure it, that kind of stuff. There are some ways you can either manipulate this formula or just conceptually think about density. If you have a very large mass and a very small volume, you end up with a very high density. So if we look back up at the equation, as our numerator gets bigger, our density will get bigger. As our denominator, the volume gets smaller, our density will also get bigger. On the flip side of all of that, if we have a small mass and a large volume, you end up with a very low density. And one of the interesting things we're going to look at is we've discussed different pairs of properties like chemical and physical properties. This week, we're going to talk about intensive and extensive properties. Density is an intensive property, meaning it is inherent to a sample and is independent of sample size, volume, mass, etc. So before we jump into intensive and extensive properties in detail, mass is very, very easy. You put it on the scale, measure the mass, and you're done. Measuring the volume is where things can get a little tricky, depending on, especially for solid objects. Last week, we talked about how to measure liquids in a container. With the glassware experiment. Now we're going to talk about measuring the volume of solids. If it's a nice geometric object, like a rectangular prism or a cylinder, then you can just use the traditional volume formulas. For example, rectangular prism is volume equals length times width times height. For a cylinder, it's volume equals pi r squared h, where r is the radius and h is the height. So you could use those if it's a nice geometric object, or at least a close approximation of one. We'll be doing one of those this week. The other option, if it's not a nice geometric shape, is you can do the volume by the displacement method. So what that means is you fill up usually a graduated cylinder with some amount of starting liquid, usually water. You add your object to it. The water will increase to a new volume, and the difference in those two volumes is the volume of your object. The object will displace an amount of water equal to its own volume, so however much that water goes up is the volume of your new object. And you'll be using a lot of that in this experiment too. Again, I mentioned that volume units traditionally are milliliters, just like we used last week, like we will frequently use throughout this course. But there are additional volume units that you guys might be familiar with. There's 1,000 milliliters in 1 liter. That one is just a metric conversion. That one you should be fairly used to, especially if you're going into the nursing field, which a lot of the students in this class usually do. You might have to deal with microliters, this last one, and 1 milliliter is equal to 1,000 microliters. So microliters are very, very small, but sometimes microliter measurements are what you need for the right balance in the human body. And something interesting that I've always found interesting is if we look back at the geometric formulas, we have length times width times height. So something that's in distance, say centimeters. Centimeters times centimeters times centimeters gives us centimeters cubed. So there's a volume unit. But the displacement method is going to give us volumes in milliliters. So how do those relate? Come to find out, 1 milliliter is exactly equal to 1 cubic centimeter. You may hear cubic centimeters referred to as cc's. So for example, in a lot of the medical TV shows, they say I need 5 cc's of something stat. They need 5 cubic centimeters or 5 milliliters. So just a little interesting fact, especially if you guys progress further into the health field. So now let's actually get into intensive and extensive properties. As I mentioned, intensive properties are independent of sample amount. They are inherent to a compound. Extensive properties are dependent on sample amount. So these are really, really easy to think about usually. if you have mass, if you're measuring mass, the more of your sample you have, the more mass you have. Same thing with volume. The more of it you have, the bigger the volume is. Enthalpy, entropy, energy, all of those are additional chemistry terms that are as well extensive properties. We won't really get into much with those as they get a lot more complex to try and measure. But mass and volume are the really easy ones. The more of it you have, the more mass, the more volume. Density, however, is intensive. The color, the odor, the melting point, the boiling point, all of these are independent of sample amount. So again, water, it doesn't matter how much water you have, it will freeze at 0 and boil at 100 degrees Celsius. Now, it might take longer to do that transformation from ice to liquid or liquid to gas, but the temperature it occurs at is the same regardless of how much you have. And so what you guys will see in this experiment is exactly why density is an intensive property. The short version is, as you increase your amount, you increase your mass and volume, and those will increase proportionally so that your density stays the same, because density is the ratio between your mass and volume. But again, as you guys watch the experiment video and really do a lot of the data analysis, hopefully that'll show up pretty clearly. This experiment is a fairly long one. There are 3 parts to it. So I want to briefly go over what you're going to be seeing and what you're looking for with each of these. So the first part, you're going to be measuring the density of ethanol, and that part is solely focused on showing that density is an intensive property. You're going to measure out different amounts of ethanol, or, well, you're going to watch me measure out different amounts of ethanol. And I'll have the mass, I'll have the volume, you'll find the density, and what you should see is that the density does not significantly change. Again, random error means all of these masses and volumes might be slightly different, the densities might be slightly different, but if they're within that, what we were saying is 20% threshold, then they can be considered close enough to be counted as the same. If they're more than 20% apart, then they're definitely different. So what you should see is as we increase the ethanol, the density stays relatively constant. Again, if you look through the procedures, it says about 2 milliliters, about 4 milliliters. You want to make sure you measure that volume out precisely to the right number of decimal places, which I will do in the videos, but if you were doing this at home or in a lab, you would want to make sure you measure out exactly to the right number of decimal places so that your densities will come out correctly. Part 2 is we're going to make a density column. So a lot of you are probably familiar with the fact that things of lighter density float, things of heavier density sink, and that's all a density column is. It's a visual representation of how all of these densities compare. So we're going to combine a whole bunch of things together. We're going to do some oil, water, a wine cork, some pennies from a decade, and put all of these together in a density column, figure out how all of their densities stack up, which ones are more dense and less dense, as well as calculating their densities through a couple of different methods. So you can really see what one looks like. Again, always make sure you're recording your measurements appropriately, which I do and will be providing for you guys. But moving forward, if you're ever in a lab, make sure you're recording your measurements properly. And the last part we're going to look at is when we're getting the density of a penny for a specific decade, we're actually going to look at how the mass and density of a penny changes across multiple decades. So we have decades going from the 1960s up to the 2000s. And we're going to take some samples of pennies from those decades, get their mass, get their density, and see what happens over time. Does the density change with time? And then there are some post-lab questions that'll direct you to, well, why do these things change? Why do you see those trends? If it's the same thing, shouldn't the density be the same? So if the density changes, maybe it's not the same thing anymore. You guys will really delve into that. But that's all for the pre-lab talk this week. Again, make sure you watch the experiment videos, and all of the other assignments and data for this course should be up on web courses. Thanks.